All right, AP Cactus AB, Unit 4, Day 6, warm up and lesson. So go ahead and try the warm up first. Any problems that you could also do with L'Hopital's rule, you might go ahead and try that too. You're going to have to do them both ways on your next test. So pause the video and try the problems, and then I'm going to go over those problems. So, all right, assuming you tried them. First one, plug 0 and get 8. Minus 10 is -2 plus 2 is 0 over 0. So it's good to show that because it tells you a lot of information. It tells you if there's a hole in the graph that you can factor out. It tells you you would be allowed to use L'Hopital's rule. So the hole is going to be at x equals 2. So we're going to do synthetic division. Don't need rational theorem because we already know the root we want to take out. 1, 0, -5, 2. 1, 2, add let's see, 4 here, add them. Should get a 0 at the end. Okay, so then this is going to give you the limit as x approaches 2 of x minus 2, x squared plus 2x minus 1 over 2 times x minus 2. The x minus 2 is the hole in the graph. Don't lose the 2 on the bottom. Plug the 2 back in to get 4 plus 4 is 8 minus 1 is 7 halves. Okay, now L'Hopital's rule would work. It wouldn't actually be that bad. It might be nicer. Limit as x approaches 2 of 3x squared minus 5 over 2. Plug 2 into this, you get 12 minus 5 is 7. Divided by 2 is 7 halves. Same answer. Okay, so next one, if you plug 0, you get sine of 0 is 0 over sine of 0 is 0. It's a whole. We can't factor the whole out of this one. I'll show you L'Hopital's rule, even though I don't think I'm going to ask you to use it on this test. But what I do want you to show is to use that thing that we've used, that the limit of sine of something of the same thing as h goes 0 is 1. But you gotta most of the time you have to make it fit that form. So I need a 3h here and a 2h here. Whatever new things I add, I got to balance out. Now the h's balance each other out. The 2 needs another 2 on the bottom, balance it out. The 3 needs another 3 on the top, balance it out. That goes to 1. That goes to 1. The answer is 3 halves. That's the kind of work I want to see. Now L'Hopital's rule, just as something interesting, I don't think I'm going to ask you to do this because it involves derivatives that we aren't really using much. I've shown you a couple. Derivative sine is cosine. Leave the inside the same. Now this thing called the chain rule, which I'm going to teach you next chapter, you're going to multiply by the derivative of what's inside. Derivative bottom, derivative of what's inside. And so now when you plug 0 into here, these are 1, right? And you get 3 halves. So I'm not going to have you guys do that in your next test, but just something to look at. Next one is we're going to negative infinity. You get squared positive square root of its positive infinity. On the bottom is positive infinity. You should get a positive answer. Okay, let's look at the dominant terms. That's the easiest way to do this. So the dominant term here is 3x and negative 2x. Now you have to put absolute values around this to ensure it comes out positive like we predicted it would. So the answer is going to be, this is going to be positive when we plug negative infinity. So that's a positive 2 on the bottom, positive 3 on the top. It should be positive 3 halves. If you didn't do the absolute values, you probably would have said negative 3 halves. You need those absolute values. Now, L'Hopital's rule, just for fun, I'm not going to ask you to do this using L'Hopital's rule on this test coming up. But this is the same thing as to the 1/2 power. So you do 1/2. This might be one of those situations where it doesn't work out great, but let's see what happens. 9x squared minus 3 to the negative 1/2 times derivative of what's inside is 18x. Derivative of the bottom is just negative 2. And so then this, if I wrote this in a nicer form, that would be the 2 goes in that. So that's 9x over 2 square root of 9x squared minus 3. And we would plug infinity in again. Negative infinity, we get negative infinity over positive infinity. I think this is just going to be a non, it's just going to keep going in circles. So it wouldn't be a good idea anyways. Okay, going up to the top, we're approaching 4 from the right side. It's going to be 8 over 0. But that means it's going to be some kind of infinity. Positive, negative. Well, we're approaching 4 from the right, so that's like something a little bigger than 4 where the x is, and that's going to be negative, so that's going to be negative infinity. Okay, that's the work you could show. It's not a whole lot of work. Infinity is going to be a positive infinity, dominant term over a negative infinity. You should get a negative answer. Now, dominant terms, they have the same degree, so it's just going to be the ratio of their coefficients, and it's going to be negative 1/2. That'd be the easiest way to do that problem. Now, we could do L'Hopital's rule. It's going to be annoying. It's going to take several steps. It should look like it's gradually getting closer to something that's determinable. This is an indeterminate form, which we're allowed to use L'Hopital's rule on. It would be a 15x squared over negative 30x squared, which would give you positive infinity over negative infinity. So you would do it again. And you take the limit as x goes to infinity, and you get 30x over negative 60x, and you would get positive infinity over negative infinity again. So you would do it again, but you're allowed to do this with L'Hopital's rule, and sometimes this is a good thing. You get 30 over negative 60, which is negative 1/2. Probably won't ask you to do something like that with L'Hopital's rule because it's just. Now this one here, I want you to do. The short way. The short way is, f of x, this is a derivative, and we're taking derivative 3x squared. And so then the derivative using the rules we've memorized is 6x. And that's the answer. So this is the shortcut, which I want you to use on your test, but I also want you to try it the long way. So if you didn't try it the long way, pause the video and try it the long way. I guarantee this is one of the kinds of problems on your next test that people are going to struggle with. So you need to force yourself to practice it. This one, we're probably not going to use Pascal's triangle because it's just squared, so you could FOIL that out in your head or on paper without too much work. But what we get when we plug h equals 0 and get 3x squared minus 3x squared is 0 over 0. So this is a whole. And so the long way is to find the whole and factor it out. So it's going to be 3 times x squared plus 2xh plus h squared minus 3x squared over h. This one's not that bad. As far as long way, this one's kind of nice. 3x squared plus 6xh plus 3h squared minus 3x squared. Now, you know the whole is at h, so your only hope is to somehow factor h out of everything on the top. The only way that's going to happen is if there's an h in every term. Any non-h terms should cancel each other out. If they don't, then something's wrong. So I'm going to factor the h out. I'm going to have a 6x plus 3h left over inside over h. That's the whole. I'm going to reevaluate by plugging 0 back in, and guess what we get? 6x, same answer. That's good time. Okay, so that was a good review, warm up. Now today we're going to talk about graphing derivatives and maybe kind of connect it to some motion problems that you're going to have questions about this kind of stuff on your test. Now, let's say we're taking a trip to LA, and let's say that, it takes us 1 hour, takes 1 hour to go the first 50 miles. Okay. And then 2 hours for the next 120 miles. Okay. We'll say the whole trip's 170. So we're starting at this is distance graph. We're at distance of 0 at time 0. At 1 hour, we're at 50 miles. At 3 hours, we're going to be up to 120, 170, because we did 120 more, right? So now, can we just like connect these lines, these dots with, sort of straight lines? That's not realistic. Okay, the slope of this is your speed. And having a corner right here, a sharp corner, even if it doesn't look that sharp, any kind of corner, And even right here, starting from 0 speed and instantly jumping to 50 miles an hour, that's not realistic either. And even when we finish, we're going 100, we're going 60 miles an hour. We got to stop when we get to our destination. So realistically, can't happen. You have to accelerate to get up to those speeds. You have to decelerate. You can't just jump in speed from one speed to another. Okay, you got to go through speeds in between, which is going to require this graph to get curvy. Okay, so more real. So if we're graphing our speed, by the way, is the slope, the derivative of that graph. And so let's just do the speed or velocity for that graph. Well, from 0 to 1, it has a constant slope of 50. So we'd say, okay, well, that's the speed. It's constant speed. And then from 1 to 3, it has a slope of 60. Now, we said this isn't realistic, but this is what this is. Now, here's the deal. This is the derivative graph of that graph, whatever that graph represents. Now, we got to put open dots because derivatives don't exist if the two sides don't agree. So any kind of corner or even the ends of something, ends don't have two sides. So, your speedometer on your car is actually, interestingly, a derivative readout. It's a derivative meter. Is that kind of cool? You've been looking at derivatives in your car. Never even knew it. Now, let's look at a more realistic way of representing this. Let's say it took us 170. Let's say we started here, at 0 and we end here. Now, we should start at a 0 slope and end at a 0 slope, realistically, to come to a stop of 0. And then we should gradually speed up and then gradually slow down. Now that's still not very realistic. A real one would go up and down a lot more as you go around curves and change direction and things like that. So, but it should be smooth, right? And distance is always increasing, okay? But where it changes, this is an inflection point, okay? So if I ask you a question, at what time are you going the fastest? Well, it's going to be when the slope is the greatest, right? When it's the steepest slope of distance. That slope of this graph gives you speed. Okay. And then the velocity graph, well, the velocity graph, now if I said speed graph, it would always be positive. Yeah, so it's always going to be positive. We'll do speed, velocity, or speed. Now, we start off with a 0 slope and we end at a 0 slope. But we're going to put open dots, like I said before. And then it's going to go, the slope's going to be going up, and then it hits that max slope, right? So there's going to be some highest point, max speed, max slope, max slope. And then it's positive the whole time. That doesn't, it goes down. That just means it's decelerating, but it still has a positive slope the whole time. Now, maybe more realistically, it might, I don't know, maybe it looks something like this, but, something like that. Not like a step function like this one. So, okay, so let's take sort of some of these ideas and just use them to help us graph just the derivative graph for any kind of function. Whatever kind of function. And this will be on your next test. You'll get some of these. So I'm giving you graphs already of some function. And let's sketch the derivative graph, okay? And so let's see. I'm going to sketch it. Now, what I would do is I'd look for really easy to distinguish slopes, like 0 slopes. From there to there, it's 0. So Now it's an open dot at 2 because it's a sharp corner, but at 4, I'd actually put a solid dot because it's a nice smooth transition. I would say the derivative does exist here. It's gradually changing. Okay. Now from here to here, the slope is up 4 over 2, which is 2. Now make sure you read the axes to know what the numbers are. Some people might think that's the slope of 1, like up 1 over 1. Well, it's up 4 over 2. It depends on how that is. So that's a slope of 2. Now I'm always going to put an open dot on the end and an open dot any kind of sharp corner or cusp. Okay. And then this looks like a vertical tangent. Okay. And this looks like a vertical tangent. So that means the slope gets infinitely steep, which means on a graph, the slope is blowing up as you get close to that. And you can't really have infinite speed, so it's going to get closer and closer to that, or whatever. So those are going to be vertical asymptotes. And here on this side, it's going to positive infinity slope, right? Now both sides are going to positive infinity, but the slope on this side is a positive infinite slope, and the slope on this side is a negative infinite slope. Negative. That's a negative slope. All this isn't. Slope here is negative infinity. That left to right is going down. Now let's estimate that maybe somewhere in here, the slope is 0 or close to 0. I don't know, it's small. And that's going to be a point. That's a smooth dot. And then the slope goes down infinitely steep. And then down infinitely steep. That's what that graph will look like. But there's a nice solid dot in there because it's smooth. And that's a peak because that's when the slope is, even though it's negative, it's the least negative, which makes it a maximum. Okay. So something like that. All right. Let's try another one. You guys try it maybe first. So pause the video, see how far you can get. Okay. See how much stuff you can get right and how much stuff you get stuck on or totally get wrong. Okay. So pause the video. Okay, I'm assuming you tried it already. Let's look for some easy slopes, like 0 slopes. And here's a nice 0 slope. And it looks like a 0 on the left side of this. And it looks like a 0 on the left side. So it could be 0 just on one side or another. Kind of looks vertical here, vertical on the right side, right? Vertical on both sides. So let's get the 0 slopes first. So it's going to be open dot here. And then there's a nice 0 slope at B, and it's going to be solid dot because that's a smooth connection. And then C, you get a 0 slope that's smooth, and 0 in between. But those are solid dots because they're nice and smooth. At E, we're going to have a 0 slope, but only on one side. So that's going to be open dot because it's a sharp change in it. F, we're going to have an open dot because it's on the end. Vertical ones, I put those in next. Okay. And then other than that, I'd say, okay, well, these are all positive slopes, right? And this is the most positive. So that's like a peak. There's got to be a peak in there. We'll make it a solid dot. And then, something like this got to go up and down, kind of something like that. And here from C to D, it blows up. It goes to positive infinity. Slope goes to positive infinity on the left. So this graph blows up. But on the right, the slope is going to negative infinity. It's the graph, it's a negative slope. So this graph's going to go like that. And then same thing here. The slope goes to negative infinity on the right side. So this graph goes like this. And that's a pretty good sketch of your derivative graph. So anyways, just throw something else in there. Speed is absolute value of velocity. Cars show speed. They don't show negative speed ever, right? So they don't really show you velocity. For the homework, we're going to not do this assignment. We're skipping it, and I'm going to give you worksheet 4-7 instead as the homework for tonight. Okay, so I just took a book assignment out of your assignments, and we're not going to come back and do it. And we're just going to try this one. Okay, worksheet 4-7, which has some problems related to this kind of stuff. All right, that's it.